Depending on your time zone, I wish you very good morning, good afternoon, or good evening. A very special and warm welcome from the slightly freezing Finland to the 6G Flagship 6G Research Visions webinar series. In today's webinar, we'll be hopefully having a deep dive into 6G networking. I'm Professor Tarik Taleb, part-time professor with the University of Oulu, working within the 6G Flagship. And I'm also full-time professor with Aalto University, where I direct Mosaic Lab. Today's webinar is truly international. We have more than 365 registrants from more than 45 countries. The map view of the geographical distribution of the attendees is truly global, and we have basically members or attendees from the different continents of the globe. So this is truly international. And this proves that networking is a very interesting and very hot topic within the research community. 6G Flagship has organized 11 white papers on different topics relevant to 6G. Networking was one of them. I'm very happy and very pleased to be one of the leader of the 6G networking white paper. And I'm also very happy to see that the 6G networking white paper has been ranked #2 in terms of hits, and it has been actually #1 in terms of downloads. So we have been attracting a lot of readership. If you have not already downloaded the paper, I would highly recommend that you download it and you read about the vision of beyond 5G and 6G networking. Here are some highlights of what we have discussed in the white paper on 6G networking. We have discussed that we need a core network which is truly access agnostic. There is still need for lots of research to make the network truly cloud native. There is need for an end-to-end service-based architecture to be adopted in the delivery of 5G and 6G networks. And we would need federating different service-based architectures through integration fabric. Definitely 6G will be supporting different services that are extremely bandwidth intensive, extremely low latency sensitive, and we would need to think about new transport networks. And this is basically we are in need of this for high precision networking. Smart telemetry, data analytics, all of these are actually needed so we can automate the network management and the service management, and we can make networks really able of self-driving themselves. All of this will hopefully lead to a new breed of micro operators. To discuss some of the topics which I'm showing on this slide, and we have actually captured in the white paper, I'm very delighted to be the moderator of this webinar where we have 4 distinguished speakers. We have Dr. Richard Lee, Chief Scientist of Network Technologies at FutureWei in the USA. We have Professor Hiroshi Esaki from the University of Tokyo. He is director of many national projects, including the WHITE project, which is one of the biggest national projects in Japan. We have Dr. Simone Redana, who is the head of architecture, management, standardization, and research in Nokia Bell Labs, Germany. He's also the chairman of the 5GPP Architecture Working Group. Last but not least, we have Dr. Stuart Clayman, who is a principal research fellow at the University of College London. I have approached these 4 gentlemen to share with us their views on how we can support 6G. Professor Hiroshi Esaki will be speaking about the different challenges and opportunities of internet towards supporting 5G and 6G. Dr. Richard Lee will touch upon the changes that should happen to IP networks so we can make them ready for beyond 5G and 6G. Dr. Redana will speak about the 5G evolution, the 6G architecture vision and enablers. And finally, we'll be having Professor Clayman speaking about how machine learning and artificial intelligence will be supporting the 6G services. Before we begin, I would like to recommend that all the attendees use full name in Zoom profile. We have also the ability for the audience to make questions, and please use the question and answer window at any time. Dedicated question and answers will take place at the end of the webinar session, and if needed, we can take one question between each presentation. We will record the webinar, including the question and answers, and the videos will be openly available on the event website. With no further delay, I would like to invite Professor Esaki to give us his insights on how the internet and beyond 5G and 6G would be architected. Professor Esaki.
It's my pleasure to be able to give my talk about the challenges, opportunity of the internet, as well as 5G and 6G, focusing on the latency and bandwidth intensive application. That's a request by the Tarik, actually. So those are my view about the challenges and opportunity about the internet, basically. First of all, when I talk with a lot of people who are working on 5G and 6G, people still using IP version 4. That's a stupid thing. Because of the large number of the end station, version 6 single stack with the version 4 as a service should be the architecture we should think about. Second one is a trustworthy. That is the other interesting and very important topic we should think about, and edge-heavy computing that should be distributed, and autonomous computing, such as the driving system or Mars system, such and such. The other one is a native digital as well as internet functions, such as the cloud native application or architecture with my understanding. Then those are the kind of architectural gene of the internet based on my more than 30 years experience about the internet. Then the important thing in this particular context today is the transparency and end-to-end, sold by the end. That is the always we are fighting with telecom people, end station versus network. So when we talk about the 5G and 6G for scalability, I heard a lot of times slicing. Though from the viewpoint of our experience about the internet, the data flow management should be individual by the end with peer-to-peer technologies, even though the cell phone network, I believe. Regarding the aggregated data flow, that should be treated by the net, such as the implicit level or explicit level, such as SRv6 or MPSSR. That is a kind of aggregated flow control. Regarding the control plane, that must be a distributed and autonomous, such as BGP operation or OSPF operation we did in the internet. So real differences from the 5G to 3G, with my understanding, three major topics. You're always talking about EMBB, very small latency, a lot of two terminals or equipments. Then why people still using IP version 4? That's a very serious and stupid thing people are doing now. And also when we compare with the telecom versus internet with my understanding, even for the 5G, client server versus peer-to-peer. Stupid thing for the 4G and 3G was tunneling to the gateway to the TCP/IP, in internet operation. And also the connection versus datagram about the signaling that is related with the latency. And then the huge terminal thing, how to resolve such a thing. Probably lifetime connection when that connected. Then why you still use the IP version for space? The other one interesting is always telecom people love SIM, not user authentication. That goes to the simple single trust. That is a telecom people love. Though we internet people love zero trust. Zero trust means multiple parameters or identifier to realize the authentication. That's a fatal thing when we're talking about SIM or eSIM operation in 5G. The other thing I want to put on the table is what is the latency contribution by EMBB, the huge bandwidth. That is the data transmission latency. That is not by the routing issue or data transmission in the wireless part. When I talk with the large size file transmission, why you need to stay long? That is the mobility thing. You can leave as early as possible when you have the huge bandwidth. That's fully related with automobile or mobile application, especially in the car application. For streaming data, you do not need to compress and decompress images. That is a quite serious issue when we're talking about 4G or 8K image and video, right? The transmission latency is far smaller than compression and decompression by budget. So when you have the 30 gig, that is, you can use uncompressed 4K, 8K with a slow, very small latency. That is my understanding about how the EMBB be able to contribute to the latency contribution. More small people talking about this. So this is really why we need such a micrometer waves. And the other point I want to share with you is the importance of the native digital from the faked, bogus digital media such as 4K or 8K. Because of those applications, 4K and 8K is just bitmap, not the fully digitized object-oriented content. So that is, I believe, 5G and 6G era is going to taking care of those new media. That is a native digital thing. The other one is the function be able to move around based on the cloud native architecture. The last one is the cyber first. That is the new way of the digital twin. That is the we should focusing on. So this is the what we are working around. You using the VR with the digital object application. Let's just see our demonstration about the such application. This is the demonstration we are doing. Virtualize the digital twin. Then you can easily change the view on the others, wherever you want. That's a kind of virtual drone. You don't need real drone. If you have such a via computer graphics space, then when you have the each flow of the sound, then you can change the view by yourself, not controlled by the network. So that is a quite important thing end to end. The clever application gonna done in the end, and also probably the network be able to help the application nearby the your terminal. That is edge computing idea. when you need a real small latency in order to the real very high response application you want to have. So in order to have the those heavy computing, important thing is the changing from Internet of Things to Internet of Functions. The function going to be virtualized like Dockers. Then the Docker virtual machine be able to mobile around you. Then those function be able to sit close to you. That is an important thing. Then this is more general idea about the say cyber first, or in the Internet with functions rather than Internet of Things. That I believe 5G has been started. Think about such a cloud computing, virtual machine, the migration, wherever the system or terminal want to do. So this is the my view about the future of the digital society. The first thing is the IoT to IOF, as I mentioned. That is really 5G and 6G is going to taking care of. So mobility of the microservice software module over the physical network, that is, yeah, I think I believe 5G is going to do. The other one is digital twin, is the one, and then going to the digital, cyber first, digital first, and conjunction with the bogus digital, that's such as 4K, to native digital. You can easily making a sound, according to your will. The other one is the siloing the subsystem, then going to the edge computing with the P2P. The initial system of the web was peer-to-peer, then the hypergiant now went to this client servers. Then the 5G or 6G coming back to the P2P, I believe. So that's all. Thank you.
Thank you so much, Professor Esaki, for sharing with us your views. Indeed, it's very interesting to see that within the internet community as well, there is this shift towards adopting service-based architecture and having this Internet of Functions concept with the mobility of the functions. This is indeed a very interesting vision. I personally enjoyed very much, the video that you showed about this live 360 streams. And definitely, now we are enjoying this webinar with more than 365 probably attendees all over the world. And the network is playing a crucial role in this webinar. So imagine that we could do it in a 360 style, in a virtual reality style. Definitely the network needs to be changed so it can support this kind of bandwidth intensive, latency sensitive, immersive services. And here I would like to invite Dr. Richard Lee, who is going to speak to us about how we can make IP networks ready for beyond 5G and 6G services. Richard, the floor is yours.
Thank you, Tarik, and hi everyone. I'm Richard Lee, and so internet technology has been very successful. It's been used to build the ICT infrastructure. And for this webinar, let me start with a very simple question. Is IP capable enough and ready for support 6G applications? We need to revise IP, upgrade it. If not, why? If yes, how should we do about it? All this is my focus in the next few minutes. And in this picture, and you can see that for 6G, it's going to be different from the previous generations. In communication technology, we start with voice communication. That would mean that you can hear something. Later, you can hear something and see something at the same time. Typically, that is video. But for future applications, very likely, you need to support more sensors. For example, touch sensors. So touch would be incorporated into your media or applications. And some people even work on other two sensors, like a smell and a taste. So that would mean that when you communicate with someone, so it's going to be all senses communications. Okay, so in the last 20 to 30 years, our top concern has always been about connectivity and bandwidth, like from 4G to 5G, from 3G to 4G. So we are talking about work out how to upgrade to increase the bandwidth. When we deploy and build the networks, we always like tout out, like how many gigabits or even terabits we are going to support. So that is bandwidth. Connectivity and bandwidth are two important legs to support ICT applications. As a result, the bandwidth is so pervasive and our society is connected now. But however, with the rise of 5G, we are not only requiring connectivity and bandwidth anymore, but we are requiring KPI such as packet loss ratio and latency. If the KPI is not met, the communication is considered to have failed. The earlier panelists already demonstrated some examples there, talking about the URLLC short latency applications. In the community, both ITU and 3GPP have documented some use cases and applications with some KPI requirements, mostly for 5G applications. Here I listed a few representative applications whose latency ranges from 500 microseconds to 50 milliseconds. In particular, we are interested in what we call low latency application, whose latency ranges from 1 millisecond to 20 milliseconds. In addition to latency, the packet loss is another important KPI. The lower the packet loss ratio, the higher the reliability. So if 5G KPI is already strict and hard to meet, but beyond the 5G and the 6G KPI would be even stricter. Now let's take a look at the current design. A packet can be lost anywhere in the network because of multiple reasons. For example, congestion, noise, link failure. In TCP/IP, after a packet is sent, a retransmission timer is triggered. The timer value is roughly equal to the round trip time. When the retransmission timer times out, the packet is considered to be lost and will be retransmitted. In this case, the latency will be tripled, 3 times bigger. The latency, packet loss, and throughput are dependent on each other. The forwarding mechanism is essentially a loop. After you send a packet, if the packet is lost, do congestion control on the sender side and retransmit it until the packet is received. The hosts implement congestion control, and the routers provide 3 base capabilities and services that are available to the upper layers: best effort, diff serve, and traffic engineering. Such a design is good enough for many applications we have seen so far. However, when we use it for business critical applications, future applications, and connecting devices that have not been connected to the internet, we will see some limitations. I list a few major ones here. Number 1, the current design does not guarantee precise KPI. Number 2, the current design assumes that one size fits all, but in reality, it does not fit all nicely. Number 3, some devices, especially industrial assets, require different addresses from the usual IP addresses. They need more types of addresses. Number 4, in the current design, the congestion control is implemented on the host. It would be more effective to let the routers proactively avoid congestion control and reduce packet loss. Number 4, holographic type communications will be a reality, will be part of the future applications. Immersive media usually require very high throughput. For such applications, we don't care about the difference in bits and bytes between the sender and receiver, but we care about the meaning and the semantics of the data in order to provide immersive experience and meet the motion to photon time requirement. We need a new type of communications. We call it qualitative communications. On top of the existing technology and features, we need a few more. In this picture, I have added 3 new features: high precision communications, qualitative communications, and free choice addressing. Many industrial applications need a high precision communication. They require in-time guaranteed message delivery, on-time guaranteed message delivery, very low packet loss ratio. If a control command arrives too late, it's useless. And so it's the machine will maybe go out of order. Qualitative communications, as I mentioned earlier, is an extension optimization of the current internet quantitative communication. And in the current internet, the user data is bits and bytes. The receiver is required to receive exactly the same as the sender sends. But in qualitative communications, it may be good enough for the receiver to receive significant components of what the sender sends. It's typically useful for holographic type of communications and video communications. Free choice addressing allows the user to freely choose the most effective addressing system for their devices and applications. Now, let's take a look at how IP was designed. You can imagine that packet format is actually a simulation of classical mail. The envelope, so the mail has an envelope and a letter. The envelope becomes a packet header, and the letter becomes the user payload. But now the postal services have changed. The user can request some special services. For example, you can ask your service provider to deliver your package over one night. Let's say send a package to ask them to send there next morning before the office opens. Now, can we follow the postal service evolution idea to design IP? I would say yes. FedEx is a typical modern courier services. In addition to envelope and user payload, a FedEx package also has an actual paper about the sender's special requirements. We imagine an IP packet as a FedEx package. The packet will have a new component which we call contract. In the contract, the user can specify some requirements for latency, throughput, and packet loss ratio. And the network is required to honor and fulfill contracts. The contract carries the performance metrics. There are a few dozens of applications that explore the idea I have just talked about, mostly in IEEE conferences and some magazines. In short summary, the IP packet can be extended and optimized in a similar way to that classical mail is evolved, so that the packet look pretty much like a FedEx-like courier packet. The major new component in the packet is a contract. Thank you.
Thank you so much, Richard. Thank you for being on time. Much appreciated. Indeed, there are lots of things to be redesigned in the network so we can make it ready to support, you know, the expected 6G services. And one of them was actually highlighted by Esaki Sensei in the beginning. So please, I would like to re-invite the audience to write down their questions using the question and answer tool of Zoom. I would like to invite Dr. Simone to give us his talk, which is going to be on 5G evolution and the 6G architecture vision and enablers.
Okay. Thank you, Tarik. So can you confirm that you can see my slides in
I can see your nice
presentation? Okay. So thank you for inviting me to this webinar and giving the opportunity to present the Nokia view on the evolution for the 5G architecture from 5G to 6G. So first of all, I think we need to understand, or we need to look at how will be our life in 2030. So we want to define, we want to look at the 6G. 6G will be the technology that we want to launch in the 2030. And then we should look at how will be our life at that time. Everything will be around, our vision is that everything will be around augmentation. So I cannot, okay. I need to move. So everything will be around augmentation, and in particular will be around augmentation coming from the digital world. So we see, for example, the capability of developing a more precise, more advanced digital twin that reflect the reality, have a mixed iteration between the real objective with the virtual objective, or with the added objective, and for this, of course, also the resolution of the mapping of the maps which are used are becoming very, very relevant. Second angle from the augmentation is the augmentation of our intelligence. So network today are basically designed to collect information, so to get information, but this information are not mostly used. So in future we see the opportunity also that those information will be then processed, will be analyzed, and AI/ML will be the tool, the enabler for this. Last but not least, it's also the augmentation towards a control, looking, for example, to robots, both on the consumer side, but also on the industrial side. So all those are something that you might also say, we can do already a lot of these already today. That's true. And that, I think, is a key point here, where, of course, we see 6G with the capability to elevate this experience to the next level, but a lot can already be done through 5G and its evolution. That's why in the enablers, in the technology enablers that I'm going to present in the next slide, those are enablers that we foresee that will allow to develop the technology needed to support the expectation that we have in our future life. But this does not mean that everything needs to wait for 6G for this. So some of those, or at least some component of some architectural components, might be already made available into the 5G evolution. So in particular, in this brief speech, I will be focusing on 4 aspects. One will be on the what we refer as at cloud architecture. So how basically we deal with a different execution environment. Run and core network convergence. So how basically the cloud native evolution of both core and the run can enable to move at the next level of convergence. Sub networks, which are very specialized network, and I will come back to those very soon. And on top of this, of course, all those new capability that the network will have then require also a new approach for the management, orchestration, and automation. So first is about the different execution environment that we already have today, and we expect to get even more in future. So, you know, we have a different type of cloud. So we have a public cloud, we have a core central cloud where today, for example, core function of operators are running. We have an edge cloud. So my colleagues before already introduced the importance of edge clouds, for example, to address a low latency application. We have even enterprise and on-premises cloud. In particular, this is also getting more and more relevance with the importance that, for example, 5G is now playing with the private network. And I want also to add here the sub networks, which are the customized network that we want to introduce and enable. But I will come to that very soon. So here we have a different, let's say, capability which are coming from the hardware with different, for example, hardware acceleration. All those capability needs to be exposed to the service, and which will then consume those. And this will also enable a more flexible functional placement, which is, for example, require to address, for example, if we want to address low latency requirements, we need to deploy function more to the edge. While if we have other requirements, we might deploy function also in the different clouds. Then another, let's say, evolution or revolution, it depends from which angle you want to see it, is also the introduction of SBA. So my colleagues already mentioned the importance of the service-based architecture. So this has been already integrated as part of 5G for the core network and for the management plane, with the introduction of the service-based architecture and then moving into towards a service-based interface. So, and we expect that this is now also moving from the RAN to the edge and to the, sorry, from the core towards the edge and the RAN. So I think it's just a matter of time that service-based architecture will be also introduced into the RAN. And this was also one of the requirement that Professor Taleb introduced at the beginning while introducing the white paper with the end-to-end service-based architecture. But having basically a complete cloud native architecture, this will enable a more flexible deployment of network function, and while having, for example, RAN and the core function, which might be deployed on the same hardware, on the same execution hardware, this can enable more optimization and more, let's say, convergence between between the RAN and the control and the core plane, the core function. Next, it's the introduction of the subnetwork. So this is an evolution of the non-public network or private networks, which are already introduced as part of 5G. So, but here we see to move the capability of those networks to the next level. So we see, for example, the capability of the subnetwork to connect a different type of device, which have a completely different function, and can be also device with a limited functionality or to a very extended functionality like smartphones or robots and so on. But we are also considering, for example, sensors, which then integrate a very limited functionality. So those are connected to an access point, and we see the subnetwork also integrated as part of the operator network, where we can benefit both from the local capability, but also from the capability which can come from the operator network, like when addressing mobility or when addressing interference coordination. This is definitely something that a more, let's say, coordination across the subnetwork can be enabled and can be leveraged. But of course, within the subnetwork, then we can have a more dedicated and customized protocol design, which is specific to the subnetwork, whether it is a body network, whether it is an in-car network, or whether it is an in-machine network in the industrial scenario. So last but not least, we need also then to look at how the network management and automation needs to develop in order to leverage all those capability. And today, most of the management of the network is basically a rule-based SON. This is what is currently implemented as part of 5G. We see already evolution of this, which is basically moving from a rule base into a cognitive network management, leveraging basically the capability, the DevOps approach. And we see also further evolution to make the function even more intelligent and basically integrate the management plan with the control plan for functions like mobility or interference coordination, and integrate also with the AI/ML execution platform. So definitely this is an evolution path, which is which we see already started today, which can be enabled by the AI/ML capability. And this, of course, can be applied to the function, to some of the function, depending on the benefit that we can derive from this. So I went through briefly on our vision for the 2030. And what are the key enablers that we see from the architectural side? Of course, I could not go much into the details, but happy to address any question about them in the Q&A session. Last thing I want to mention is that we publish, or my colleagues have recently published a book which is addressing exactly this evolution of the network management from a rule-based to a cognitive network management, and I would recommend you find more details in the book.
Dr. Redana, thank you so much for the excellent talk. I share with you the views that definitely cloud has been playing a crucial role in the design of 5G, is going to continue to play that role in beyond 5G as well as 6G. If I have to make a mathematical equation, for me, 5G equal 4G plus cloud, heavy cloud presence. And if I have to make it 6G, then it's going to be 6G equal 5G plus AI, artificial intelligence and machine learning. And this takes me to the last but not least talk, which is going to be given by Dr. Clayman. And it's actually about machine learning and artificial intelligence in support of 6G service and 6G system. Clayman, floor is yours.
Thank you very much. Right, let me turn on sharing, screen sharing.
Meanwhile, I would like to remind the audience that all the material will be shared on the 6G Flagship website. Videos will be also published on YouTube, so no need to ask those kind of questions. Please feel free to ask technical questions that we will be hopefully addressing right after the presentation of Clayman. Thank you.
Thank you, everybody. So originally I was asked to consider how new transport networks and AI can support these new expected immersive services that everyone previous to me has talked about. And it's an interesting title that covers many areas. And I was looking at it thinking, what does all this mean? There's so many questions. What are immersive services? How do we even create them? How do the networks evolve to support these? I know Richard's been looking at these for a long time. How do we manage these services? And what is AI? People talk a lot about AI, but what systems do we need to support all this stuff and have AI? And how do all these new elements talk to each other? And just thinking about these questions made me realize that this was not a talk for 10 minutes. This is an hour, or maybe even a whole book, as Simone just mentioned. There's a huge amount of stuff to consider. So I thought just for this talk, I'd concentrate on some of the AI parts, because it may help focus people's minds on where we are and where we're going, and some of the important aspects that need to be addressed. Oh, hold on. If only I click the right button. No. Oh, there we go. So let's start with something very important. People talk about AI and machine learning, particularly these days, as though they're identical things. Historically, they're not. AI and machine learning have some relationship in a certain branch of computer science, but they're based on different foundations and different approaches. And I wanted to highlight this to people because it might, again, might help focus your mind on what's happening when people say AI and talk about something. Oh no, that's different. So really, in my mind, artificial intelligence is about the mechanisms for reasoning about stuff. You have state, you have rules, and you reason through it. The state of the world is represented by models that are called knowledge representation. And you can look at a piece of knowledge, a data structure, and you can say, my AI system knows this about the world. You can point at an individual rule and say, this is a rule, it will determine something. I can look at a piece of data and say, this piece of data represents something in the world. Machine learning is more like statistical probabilistic predictions using neural networks, various machine learning. You cannot point to a node in a neural network and say, this node means this, in the same way that you can a piece of data in an AI system say, this data represents this piece of knowledge. Now, the important thing is that over time, the machinery for dealing with this stuff has got better and better and faster and faster. And as I've got in the last point here, the creation of cheap GPUs, TPUs, bespoke chips has meant that machine learning mechanisms that used to be hugely expensive and only available to a handful, you can suddenly run on a cheap laptop. And so all these introductions of ML techniques you've seen over the last 5 to 8 years are a side effect of all this stuff. But it still means that ML is ML and AI is AI, in my mind. So, no, still doesn't like it. Right, next one. So now we've got these two techniques reasonably related. We have to ask ourselves, how can AI and ML really be effective in our new enhanced network? And we have seen some advances over the years. We've seen a lot of papers about it. But how do these existing technologies that we have, NFV, SDN, new services, how do they feature with respect to this AI and ML? And how are you going to manage all these in this context? So it leads to the next question. Is it better to adapt the existing components we've got? Because in many network systems, these components are huge. Okay, there's 10, 20 years worth of development in some of these network service management systems. Are we suddenly going to bolt on all this new stuff, or should we devise new ones? And then that leads to the last 2 points. What are the abstractions? What are the knowledge representations if we're going to do AI? What kind of machine learning techniques are we going to do on this data to do predictions? And what happens once we've got it? We've got all this stuff. We can use different kinds of induction, explanation systems to explain to end users what's happening, why it's happening. These are all the holy grails of artificial intelligence. So in terms of AI and ML, we need to think about it in terms of management of next generation systems based on 5G and 6G. We have to orchestrate all these software-based things, SDN, NFV elements, Again, all the abstractions, the knowledge. What is the data? Semantic models. We can do reasoning about error conditions, normal conditions. Maybe we can create automated actions to avoid having manual intervention. We can use some of these techniques to overcome the running of scripts. I know, talking from many network operators, the network's run by a bunch of scripts. Something new happens, oh, run a script. Well, you imagine you got all this stuff. Maybe we can overcome some of these kind of self-limiting capabilities. And of course, the last one, which feeds in some of the previous talks, we got monitoring, telemetry subsystems, vast amounts of data. What do we do with it? How do we deal with it? And this is where AI and ML is considered a good area. So something I want to highlight in particular, so one of the major innovations will be this idea of this distributed intelligence, where you have multiple specialist components. Some may be using AI, some may be using ML, that you can build together to combine their expert capabilities into a single system. So each component will be specialized for one job, but they'll be connected together. So you have AI components dealing with representations and doing reasoning, ML components looking at larger data sets and learning. And so what we'll end up with, possibly, is a system that looks like this diagram at the bottom here. So these blue ones are meant to represent artificial intelligence thing. I call them intelligent. So you might have the intelligent virtual link analyzer. It takes some data, does some analysis, and sends on link J should be moved. Or something to do with the cloud, looks at virtual machines, physical machines, virtual machine R is out of memory. That's all it decides. Doesn't need to do very much. They're specialized and they work together. And what we have in the center, which itself might be its own distributed system, which borrows from AI in the past, is this distributed blackboard mechanism. Why do we have that? It means that the special components can all generate data that they see individually, and we can have some other component which reads this distributed blackboard, let's call it the zero-touch manager, that gathers the deduced, inferred, learned knowledge and makes decisions about the systems that we need to adjust. So we might say, let's adjust the base station power. We'll talk to a base station power actuator to actually make it happen. Let's talk to a link actuator, service actuator. So we have this separate systems, all talking to each other, all intelligent, and another manager dealing with it, and you end up with this real-time loop. Okay. So now I want to come towards the end. We have to think about, well, we got all this clever stuff, but, well, we need to deploy it. But then you go, oh, hold on, there's all this stuff to do with softwareization, programmability, all these things. They're often presented as different methods. They kind of are, but they're not really independent. They're intrinsically linked as they all operate on the same elements in the network, the same services. It doesn't make sense to have deployment of multiple independent systems all talking to the same stuff. So the consequence of this is that you need I'm talking. Can you answer the door? Mark, I'm talking to people over the world. Sorry, there's someone at the door. Can you please answer it? So yeah, so we need all these abstractions and runtime systems to deal with this stuff. Okay. So what are the conclusions? I believe that intelligence will appear more and more in the different layers and more in the network management systems. We'll have new networks, new network paradigms, new services. We'll all use AI and ML for their operation. But an important point is that we can't really have machine intelligence if we don't have representations about all the underlying elements to reason about. You can't reason about things unless you can represent them, and you can't do learning unless you understand the structure of some of the data to understand what's going on. And of course, for that full loop that I mentioned, you need a level of flexibility and dynamic control to make these things happen. Otherwise, you don't have the full control loop. And finally, it's clear that these AI and ML methods will be used for the new transport networks and the new services that will become available to us in the future. Thank you. That's the end.
Thank you. Thank you, Dr. Clayman, for this insightful talk about how AI ML can be used for supporting 6G system, 6G services. I fully agree with you that we need this kind of distributed intelligence and somehow cross-system AIs. We should merge intelligence from different segments and come up with the right decision, for the end-to-end connection. So with this, we had 4 excellent talks by our 4 distinguished speakers. We have been actually receiving quite a number of questions. Some of them have been already answered live by our speakers. And some of them, they have been actually, the panelists, they would like to answer them live. So let's shoot. So the first question, which I would like to take actually, although it has been answered by Esaki Sensei, I would like to take live. The first question was actually, who is going to be the host of this different Internet of Functions? Esaki Sensei.
Yeah, I briefly responded to the question, though the problem of the, say, cellular phone network is its transparency. The meaning of transparency is wherever you put the, the node, that is the basically the internet design. And also, I believe 5G has the quite similar capabilities are going to provide. So if you have the very transparent, say, data flow network, then you can put any function wherever you want based on the virtual machine. That's a cloud native function, as the few speakers speaking about. That could including AI function as well. Then you can get kind of virtual network. Then who is the host? Host could be end station. End station including cloud service provider. That is the understanding or architecture concept of the internet. Even server or client, that is end station. So the end station be able to provide any function wherever you want. You can put the function if the node has the capability to be able to accept those, functional module, meaning executable platform.
Thank you. Indeed, this takes me actually to one of the questions that was asked by Professor Matti Latvahu, who is the director of the 6G Flagship. When we have these functions running on virtual resources anywhere in the world, on any kind of heterogeneous cloud, as Simone has mentioned, vendors, network equipment vendors, they make lots of money out of selling those expensive nodes that are actually running on dedicated hardware. So by making these kind of functions virtual, running on virtual resources, here I'm asking a question to Simone as well to Richard, representing two giant vendors in the world. Do you see any potential risk for vendors there? Do you see the operators ready to accept this drastic change in who is going to own what? Richard or Simone?
I can go first. So if Richard is fine.
Go ahead, please.
Yeah, I mean, I just want to emphasize that we are not only, our business is not only related to the hardware, but is also very much related to the software. So of course, I mean, the historical part of our business is coming from the dedicated hardware, but in the last years, this has been also expanded more also in the software domain, and this is also going to happen more in future. So I would say I think all the players have understood that there is now that the trend is even more and more towards a cloud native, and then we are supporting that and really working we see a business there as evolution of our business that we had a few years ago, and we are continuing to do that. So
thank you, Simone. Richard?
Right, so any big changes to the network and services. And so according to my experience, I have talked to many European and UK customers there. It's going to be difficult. There is an inertia there. There is a resistance there. So but it also depends on what you are talking to, like a technology strategy guys may like it. But finally, if you put in their production network, it's very difficult. So that in the end, so the formula, the cost, benefits, the balance here is important. So when we say changes and dramatic changes, right? It always depends. When they say big benefits, when the benefits outweigh the cost, they're old. For example, when they upgrade, they move network from 4G to 5G. The cost is huge, but the benefits are also huge. So in that case, they will upgrade. But for other services, we need to talk about case by case. In general, customers, operators are very conservative. So you have to show them with the money, yes.
So you admit that the operators are still conservative?
Are very conservative, and also the initial resistance and always plays there. So I talked with a particular customer, right? And they told me that they were very brave, invested a lot. So right now they have big financial problems because they introduced something they have heard from a particular vendor. They put it in their production network. After they put it, it's just not technology. They need to train people to operate their networks, right? So the training, set up a new department, troubleshooting. So it's a of course it depends on which feature, which function, which requirements and application.
Thank you, Richard. A question to Stuart. When we combine multiple AI and machine learning systems, which is the vision of distributed intelligence, aren't we going to lose in terms of reliability and interoperability? Do you see any risk there?
It depends how you put them together and how the control elements that use that data work. In the design I presented in the slide, they use this distributed blackboard model. So they're very loosely coupled. So the individual elements are specialist, they take their inputs, they do their outputs, they send them to this blackboard, and they're done. They have no interaction directly with the actuators. They're just there to either run rules, do some intelligence, inference, or some learning as to what's going on. They pass it on and they leave it to a bunch of other managers, processes to deal with it. So much like in the way that you might imagine a human being, our eye subsystem, hearing subsystems, smell subsystems, they're all independent. They do stuff, the sensors work, they send messages to the brain, and there's bits of the brain that deal with it, and there's actuators to do stuff. Now, it's a very simplistic model, but that's how I see it as the best way forwards. If you try and integrate them all, tightly couple them, and they all directly interact with each other, then I believe you're prone to go down that road of mess, failure, instability. So it's better, in my mind, it's better to have this loosely coupled mechanism.
Do you foresee any conflicts between the intelligence that could come from different segments? Say, for example, the drawing that you used, the system would say, okay, certain VM should be moving from a cloud to another cloud because you have enough resources there. But then the link to that cloud could be not sufficient enough. So you've got here two.
Yeah, I mean, absolutely. But then you already have the same issues. You already have a lot of these issues. So I don't think that AI or ML will make existing issues go away, because I can still make that decision. I can still write some algorithmic thing that makes equally bad decisions, or can make a decision and not know that the network is congested. And why does it not know the network's congested? Because operators will hide the status of their network from outsiders. So a few years ago, we were writing some cloud software, and I wrote some software, go, right, let's send a VM to another cloud. And both clouds, remote clouds, could tell me their exact status and how much capacity they had, but I could never find out what the capacity of the links between my cloud and the two others were. Couldn't find out. So then I was left with a random decision as to which cloud to send to. But in reality, one of them might have had a very congested network. And if I knew it was congested, or they were able to tell me it was congested, I wouldn't send a large VM down that link, because it's a bad decision to make. And so you end up with a kind of layered solution, really. What should I know? What could I know? Am I making the right decision? Is it the wrong decision? And I don't think AI or ML really cuts across any of these aspects, personally.
Thank you. Professor Esaki, the vision of Internet of Functions, which is combined with this concept of service-based architecture in 5G, and definitely this is going to continue in 6G. This is going to lead definitely to a very complex system. And here I would like to read this question of Matti, although it's put in the context of AI, but it's in general. One fundamental challenge in any complex control system with nested loops is the overall stability. Isn't stability going to become possibly even bigger issue? You know, when you talk about Internet of Functions, when you talk about core network being virtualized, everything is being virtualized, running on systems which are not actually reliable. And then you give the task of management to these AI and machine learning agents. Do you see any stability issues there?
Well, question to me?
Yes.
Well, yeah, basically, the answer against the question by the Stuart was the say triple function authentication or triple function can be charged to the users in order to protect the quality of service. That's usually the function of the operating system in a single hardware system. Though that is already done in the large cloud network by the hypergiants. This is providing the enough bandwidth between the processes. That is yet another business done in the huge cloud network by the definition of the hierarchical topology configuration in the cloud backbone. So similar thing gonna be applied in order to making enough bandwidth between the processes. That is the say probably the AI could providing those function. Then even though you must maintain the status of the resource in order to provide enough quality among the functions. Once again, that is fully done in existing cloud network.
Simone, would you like to add anything to this?
No, I think Professor gave a good answer also from my perspective. So
excellent. So now I move on and I ask question to Richard about new IP. The question says, I'm wondering how does new IP address address such issue as IP overloaded multi-homing mobility? Shall we introduce a new namespace which is location independent for end host instead of using IP addresses plus the port to bonding? Well, it's a very technical question, and I'm sure that Richard, you're capable of addressing this question too.
All right, yes, thank you very much. It's a really good and very technical question, right? So if you still remember when I outlined the framework of the revisit, IP, revised IP there, so you probably see that I didn't say we are going to take a particular addressing system, right? So it is pretty much like FedEx package. In FedEx package, they provide you envelope and a slip, that's a contract. And the user will put their payload, like later or something else. Then they fill out the envelope. So in the envelope, the addresses could be different. For example, suppose Professor Hiroshi sends me a letter. So his home address, I assume, will be written in Japanese. My address, destination address, would be written in English, right? So the FedEx provide you package. They are not going to say you have to use which addresses, right? So the user will feel free to use the most effective and valid addresses. So that is, so new IP in this IP system or revised IP or new IP here. So we don't exclude any possibility. We give this freedom to the user. That first thing there, and I should make it clear. So the question also asks the multi-homing mobility IP overloading, and that's true. Currently, IP address and semantic is overloaded because it has two meanings. The first meaning is who you are. Second meaning is where you are. So we send a packet from A to B. Actually, the B is not only the location, it's only the who you are. So like Cisco has implemented technology. They are using the ID and the location separation there. So it's called Lisp there. So it's all deployed. So that's the ID-based technology there. Multi-homing is still the same thing and similar to mobility. So you have the double addresses. So in this new IP, there is some way to address mobility there. So because it will can encapsulate your older addressing system in the new one, like in a postal service, you go there to tell them you have moved your home. Actually, you can register that. After the post office receives such a letter, they will deliver that to your new address. That is possible, but it's so technical. In 10 minutes, I took that out. So the short answer is yes, we can do it. And also, so for addressing part, so new IP doesn't define any particular addressing system. We give the freedom back to the end user. Thank you.
In this concept of new IP, you've spoken about one of the key aspects of it is the concept of contracts. So contract-based delivery or contract-based networking. One of the questions was asking how this contract of new IP work. Is it similar to smart contracts of systems like blockchain? Can it also be used, to enforce certain level of trust and liability?
It's another good question, also very technical. But first of all, I have to apologize. I'm not expert in blockchain, so I cannot comment on that myself. But for the trust and the liability, and there is some work here. So we call that the intrinsic security. So if you look at the current network system, so the security was added after thought. So after your network is designed, you add another layer. So typically in a transport layer or application layer. So they do that. So we can use that to do some trust here, and also for some specific applications, especially for industrial application. If you're familiar with a Profinet, that's industrial like automation and network. So each device, machine, is controlled by another machine. Typically, it's a software we call the PLC, Programmable Logic Controller. So machine would know that who could control me right? So nobody else could control me. Otherwise, like something would be wrong. So somehow here they can build some relationship here. So if the like POC like says something, so the your machine may ask some question, right? If the answer is correct, is not correct, so the induction machine would shut down the communication because they know that the machine should not listen to the pre-designated PLC than others. So there was something there. It's an intrinsic security. It's security is built into the network layer, but this is work still going on. So, and moreover, it's not affected the kind of framework there. So there were some tests there for the limited domain in an industrial application, and it works. But that's not for general application, but not for like a banking, shopping, that kind of security. For the liability here, it's I was also asked question here, but I would say that that's more a business issue. Let's say if my packet is lost, you give me a refund like a package does. So actually that happens before you deliver the packet to your FedEx office. But in the packet itself, it's not technical like issue there. So I'm designing routers there. So, but if people have like better idea, good idea, and I'm open to discussion, and we can talk about it later offline.
Excellent. So security by design, liability by design possible, but not,
Yeah, some of them, yeah, like liability are more business issue, not technical issue. And
all right. So Simone, one of the, when you spoke about the 6G vision, most probably of Nokia, you spoke about three elements: heterogeneous cloud, this convergence between the core network and the radio access network. And the last point was this sub-network. And in my opinion, if I understood it well, it's the concept of micro operators, right? Small scale operator for smart factory and so on. Now, the question is, the introduction of these kind of customized networks would be limited by operators owning the spectrum unless drastic changes happen or are introduced in the future spectrum regulation to make it independent from the current owners of the spectrum. Is Nokia going to drive this type of changes in the future? A very big question, but Simone.
Yeah, I partly address already in the Q&A, but maybe let me explain. So I think this was also one of the main point discussed already part of 5G. So when we started to introduce the private network or non-public networks, I think the availability of spectrum was bring up, and at this point is I'm sure regularly is coming back. But when looking to the spectrum, I think there are already today opportunities for spectrum which can be used for private use, or for industry use, or from in the future also for the sub networks. So just to think, the example that I put in the Q&A is the 3.7 gigahertz, where in Germany, where 100 megahertz has been allocated for private network use. We have other cases. So if I look, for example, to Japan, there are 100 megahertz which have been allocated already at 28 gigahertz. So it's called local 5G. And I think also soon there will be other 100 megahertz that will be allocated also sub-6. Or in US, there is, for example, the CBRS, which will enable. So I would say opportunity for spectrum usage, which will be then more for operator or for, let's say, enterprise, are there. And so I don't see this really as a showstopper, let's say, to enable subnet or private network or a new, let's say, or local application in future.
Thank you. Clayman, there is a question which is about AI, so I would just address it to you. The question says, is there is there a platform that you can use for artificial intelligence, machine learning? What do you think about Kubeflow?
Kubeflow, I don't know. I guess
Maybe
from its name, it's
TensorFlow,
some
maybe.
kind of Kubernetes kind of Dockery kind of on the fly system. Well, the thing about AI and machine learning, there's multiple systems, multiple platforms. They each have their own specializations. This is what's good about them. And this is one of the reasons why I said earlier in my answer, you should have loosely coupled things. You should not imagine there's a one size fits all AI ML platform. You should build it in tools that work. You know, if you're doing machine learning, you should have a machine learning package. If you want to do neural networks, you should use a system that's designed for neural networks because they do it well and fast. That's what never happened in the past. So build your system on the tools that match what you're trying to do, and then deal with the integration later on.
Thank you. Esaki Sensei, you want to comment on the question which was about smart contract by blockchain and how it works within the concept of new IP that Richard spoke about.
Yeah, basically the smart contract defined by the EtherVM is the defining the kind of function among the entities defined by the contract, meaning the each node, each function be able to the module to construct the network of the contract. So that is similar to the idea of, say, service functional chain. That's again IOF. So in that case, the carrier service may be able to provide the authentication or authorization thing in order to protect the correctly execute the contract. That is kind of service overlaying over the 6G network with my understanding. Once again, that is going back to the function, going to be functions, any function be able to connect it to each other based on the contract defined by the blockchain.
Thank you. Now I have actually a question from my side to all the panelists. And actually this question I got inspired from Richard presentation, the keynote that you gave at GlobeCom in Hawaii. You spoke about this use case of you have a concert operating on site in say Las Vegas. Half of the orchestra is on site, the other half is teleported from Paris. And then you've got some dancers that are actually dancing in New York, but they have to be teleported in real time to Las Vegas so people can actually enjoy that show. And here you're speaking about teleporting half of the orchestra, and it has to be really the music, because this is all about music. Everything should be well synchronized. They need to be teleported from Paris, from a continent to another continent, to Las Vegas. And then the people that they are dancing from New York to Las Vegas and their move have to be really synchronized with the music and so on. For me, when I was thinking about this, I thought like this is really, if you can bring a system, if you can build a system that can actually support this use case, I would call it, that's it, that's the end. That's actually the last generation of mobile communication systems. Do you think that this can be really the 6G use case that the 6G community can aim for? Question to each of you guys.
Okay, so if
maybe Richard, because it was your use case, so maybe you're the last one to speak. Simone, okay. Esaki, and then Clayman, and then you.
Okay, so I'm the pleasure to be the first one. Yeah, I agree that this is definitely one of the challenging use case, because here you have really a combination of let's say you need to synchronize across region, and which have of course a different impact on the latency, because we are always saying that in order to support low latency you need to have application into the edge, But I think here you have you cannot really rely on this network configuration. And the second, you have also the synchronization between audio and video, which I think is one of the most challenging requirement, because it goes down to really a sub-microsecond. I mean, I'm not an expert in the area of video production, and but I know that this is one of the most challenging. So I would say I think 5G has already some enablers which can allow this, like the support of low latency, like the support of the integration of time synchronization network, TSN, or let's say more native time synchronization support, which is part of 3GPP standardization. So with the start in release 16, with the introduction of TSN, and then with release 17, for example, with the support of IP, which is what is used for the video production. So we have already the enablers, but I think what we are not, we cannot achieve now. We might not be able to achieve the requirements for this use case. Then coming back to my point, whether we will be able, we are working on 5G and on its evolution. A lot of technology components and architecture enhancement that I presented, I think they can already be introduced as part of the 5G evolution. Then I would like to challenge you back. I think 5G evolution can still address this use case. If not, then we will look at 5G for sure. But I'm still convinced that we can evolve 5G significantly and meet the requirements of this use case.
Thank you, Simone. Esaki Sensei, you said that 10 years back, you did a remote concert between New York, Tokyo, and Zurich in 2005. So you don't have to work on 6G anymore. Esaki Sensei.
Well, at the time, we have the very, the first link among the Tokyo, New York, and Zurich using the R&D network. Then, fortunately, classic music players have the capability to be able to adapt with the delay of the playing. The conductor having the pace, the player having the fixed latency when they play. That's our understanding when they talk with them. If the fixed latency is going to be created, then they can play. That was the players have such a capability. The other interesting thing was the music composer start to think about, if there's a latency, they is going to making a new music. Positively using those delay in order to make a music, interactive way. So that is just musician can have the completely different delay environment. That's the new artistic challenges that we understood.
But if we add to it like dances that are really dancing in a certain style, which is very dynamic, and you need to teleport them and so on, I think it will be very challenging, in my humble opinion.
Yeah. So that is good for the musicians or composers. The other thing is because of the end station has a lot of power, so they could playing by the anticipation by the AI. Probably the AI be able to making anticipation, say 500 milliseconds. Then that's able to provide in those say not the real, but as small, close to real reaction by AI.
What do you think?
Yeah.
What do you think? I mean, he's bringing AI into this use case.
Well, I don't know. Interestingly, at UCL, we've made some advances in some of the elements that might help Richard's use case kind of come to fruition. We've done some work on sending scalable video using big packet protocol into the network. We've got some very good results in terms of delay and responsiveness, because the interaction between the network and the big packet protocol and the way scalable video can be encoded into packets means the response time and the way loss is dealt with in terms of removing certain chunks of data has been very good. And we're writing some papers on that at the moment. We've also been looking at a similar use case to the one you just mentioned in terms of synchronized streams of multiple interaction and what some of the network requirements might be. I think the most important one I should mention here is that we realize that somewhere in the network, there should be some kind of stream synchronization, because the network needs to support sending these multiple streams in some synchronized way, knowing what the time synchronization is, and that actually the network should throw away the data if things become desynchronized. Otherwise, you just flood the network with data that's going to get to the far end and just be thrown away. Maybe the network can even support resynchronization. So there's a lot of interesting things to do with what does synchronize mean? What's the time window for synchronization? It's very, very difficult to do the scenario Richard mentions if the network has no concept of time windows. It can't be a packet at a time delivery. And we could talk more about that anytime. And the last thing is we're looking at is this enhancement to the socket, the way applications interact with the network. Currently, it's like oil and water. You have the application space, you have the network space, and you have this tiny little connector called a socket, and they're very unfunctional and very limited in their options. And we're looking at ways at which the application can ask the network information before it sets up a socket, and also to tell the network stuff in advance. Look, we're going to be sending stuff, please sort yourself out. Because at the moment, most stuff's packet at a time. And we believe that all these enhancements and all the things we're looking at can get closer to where we are today towards this use case that Richard's previously mentioned.
Thank you. Richard, you mentioned this use case exactly 1 year ago in Globecom Hawaii, and actually now Globecom is taking place. So in this last year, have you made FutureWei or Huawei, have they made a baby step towards realizing this baby or giant man step? I don't know.
Thank you. I also like to thank Stuart, and I was extremely happy about his implementation results about the large scalable video communication he just mentioned. He also mentioned the bigger IP protocol. By the way, for those who do not know, bigger IP is a preliminary version of new IP. It was published in ACM SIGCOMM workshop in 2018. That was 2018, right? So probably 2018. So it was 2 or 3 years ago. And so I did mention this like a example in my Globecom keynote speech last year. And I believe that holographic type of communications and holographic teleport are really challenges, and 6G should and will make it a reality. But there are multiple levels of challenges, right? On the media side, you have how to capture the image, put it in a holographic packet. In the network side, how are you going to teleport it or transport it? So that how will you generate a holographic image, there. But these are three big tasks there. But before you display them, you also need to synchronize. Here it's not one point to one point. It looks like pretty much like a reverse multicasting from multi-point to one point here. So in 1 year, we have made a progress here. So I have mentioned a qualitative communication there. So one challenge is that, so in the current internet, your packet size is limited by MTU. It's 1500 bytes usually. But because holograms are usually big, suppose some people dances there. So in 1 second, you need to transmit 30 frames. At least like for video, you need to transmit 24 frames there. So if you lose a packet, so in the counter design, either you retransmit it or just accept the loss, right? So there are some issues there. So when you compose voice, dance, and piano like there, so there will be some issue there. So that's why I mentioned a qualitative communication added to the this new IP framework. So we have also worked out some other examples like a multi-camera from the vehicle. Like in Tesla, you have 8 cameras. In Waymo, you have 29 cameras there. So our kind of progress is mainly about the encoding of the packet using the like a jumbo frame or the baby jumbo frame and in the optical layer. So our major challenge is on the synthesize side there. So how do you need to encode them together? But we have published some results, mostly in I3 conferences. Also this year, we also received the Best Paper Award from one like media related conferences there. So I'm happy to talk more about this later offline because it's quite complicated. But what I can say is that the problem is not completely solved because there are multiple levels of problems there. We only solved partially. I would say we may have made a step in the networking side, but in order to put them together, there are multiple sides. But I heard some story from Surrey and University of Surrey. They have implemented a very good prototype there. It's a holographic prototype, and it works. There should be some like very preliminary like experiment, but I haven't seen yet in person. And so let's wait and watch. But still, in order to make 6G happen, it's still like 10 or so years away. So there are a bunch of time ahead of us. Let's work harder to make it happen.
Thank you, Richard. Thank you, actually, Esaki Sensei, Richard, Stuart, Simone. Actually, there are lots of other questions that I would love to ask you and also the audience, but we are already 7 minutes, above time. I would like to really take this opportunity to thank you again for, accepting to be on this webinar. I hope that the audience have found it fruitful and insightful and inspiring for their research work. So with this, I just have a few points to share with the audience. I hope you can, do you see my slides, I hope? Hanna, can you confirm that you see my slides?
Yes.
All right. So basically what I would like to say, I would like to invite the audience to keep, stay tuned and register for the next 6G Research Vision webinar. The next one is going to be on a deep dive into the white paper on radio frequency enabling 6G, opportunities and challenges from technology to spectrum. We will share, the slides. We will be sharing also this video once it's been edited, on different social media, on YouTube, and also we will publicize it across different social media. These are actually some of the hashtags that we use. Discussion will continue, and please stay tuned in 6gchannel.com. Once again, thank you for the panelists for being on this webinar. I think it's getting too late for Esaki Sensei and also for many people, attending from the other side of the world. It was a really pleasure to be here moderating, this webinar on deep dive into 6G networking. till a next opportunity, I wish you all the best. Thank you.
Thank you.
Thank you.